In this video, we are going to discuss one of the basic heap operation, that is insertion in a heap. So, if an existing heap is there, how we can insert a new element into that heap. So, first we will see one example. So, suppose we have one existing heap. So, that means the heap is like this: 80, then 40, then 70, then 40, so it is 45. So, this one is 45, 45, okay. Then it is 35, then 50, this one. So, this is an existing heap. So, you can verify the properties. So, all the properties that we have discussed here. So, complete binary tree and the parent child relation is satisfied here. So, we can say this one is a heap. So, now we want to add or insert one element into the heap. So, here you can see, if we want to add one element and the element value is, so assume 90. So, if we want to add the element 90 or insert the element 90 to this existing heap, so where should we add? So, the new element always inserted at the end. So, here only the right child of 70. So, if we continue like this, so let me move this one here little bit. So, now this 90 is added here. So, let me draw the figure here. So, it is 80, then 45, then 70, so 40, 35, then 50, then here it should be 90, the new element. Now, here you can see, when we insert 90 here at the end, the key value of parent, that is 70, is less than its child key value, so 90. So, 70 is less than its child value 90. So, here is a violation of the heap property. So, what should we do? So, we should replace or exchange the values of 70 and 90, or we should swap the 90 and 70. So, if we swap, then what is going to happen? So, if we swap like this, so the next, here you can see, it will be 80, then 45, then 70, then 40, then 35, now 50. So, we have to swap these things 70 and 90. So, in place of this 70, the value should be 90, and here 70 will be there. So, I hope all of you understood this one. So, we are simply swapping to satisfy the heap property. Now, when we swap, here you can see, after we swap the values of 90 or 70, 90 and 70, or we exchange 90 and 70. So, here again the heap property is violated in this part. So, the parent value is 80, child value is 90. So, what should we do? Again we swap. So, again we swap here. So, if we swap again, so you can consider this one. So, the new structure. So, we are going to swap these two values. So, 90 comes here. So, 90 comes here. Then left child is 45. So, its right child should be 80 after swapping. Then for 45 it is 40, 35, then for here it is 50 and 70. So now you can observe we have, after swapping we got this tree, or we have this heap or complete binary tree. So where the heap property is satisfied. Here 90, you can see the key value of parent is greater than 45, 80. 45 is greater than its children 40 and 35. 80 is greater than its children 50 and 70. So when we insert this new element 90 here to an existing heap, so after insertion we got this as the final heap structure, or this heap changed to this one after insertion. So how we are inserting? The first step is insert at the last here. Then after insertion, verify whether the heap property is satisfied or violated. So if the heap property is violated, swap this value, the newly inserted value, to with its parent. Similarly, after swapping here, so here you can see, after swapping, again check whether the heap property is satisfied or violated. So if it is violated, again swap with its parent. So like this we will continue until we reach the root or the heap property is satisfied. So we will take one more example on this. So I hope this one is clear to everyone, this example. So we will take one more example on this. So here you can see one existing heap is there. So always we are inserting the element to an existing heap. So we have another example. So 20, then 15, 7, then 5, 3, 1, 6. So this is an existing heap. So here you can see the property is satisfied, and it is also a complete binary tree. Now we want to insert, assume 18. So we want to insert 18. So where should we insert? So at the last means this level is completely filled. So we have to insert 18 here to the left of 5. So if we insert, so the figure will be, or the structure will be like this. Here you can see. So let me copy the structure once again. So this is the existing one. Where we have to insert? We have to insert at the end, that is here 18. So now after insertion, check whether the property is satisfied or violated. So if the heap property is satisfied, then no issue, no need to exchange. So if the heap property is violated, then we have to exchange. So here you can see, after insertion of 18, here the heap property is violated. The parent value is 5, child value is 18. So here we are considering max heap. So for min heap, the same procedure you have to apply. So here you can see the parent value and child value are not satisfying the heap property. So we have to swap or exchange these two values. So if we exchange these two values, what will be the new one? So let me paste this one here. I have earlier copied. Okay. So this is the tree, and we are inserting 18 and swapping. So if I swap here, so 18 comes here, then its left child will 5. Simply I have swapped these two values. So if we swap, 18 comes here and this 5 comes here, and the others will be same. So here you can see 18 is here and 5 is here, and the rest are same. No change here in this part. Now again we have to check after swapping whether the heap property is violated or satisfied. So here you can observe the heap property is violated. So 18 is greater than 15. So again we have to swap. So if we swap again, so here 20, then 18 comes here, so 18 comes here, then its left child is 15, then right child is 7, 1, 6, then 18, 3, this is 5. So here you can check again after swapping. So we have swapped this 15 and 18. So we have swapped 15 and 18 here. So this is the result of after swapping. So now after swapping the key value with parent or the child value with its parent, then check whether the heap property is satisfied. So here you can see heap property is satisfied. So heap property is satisfied. Heap property is satisfied. So no need to swap again. So if the heap property is not satisfied, then we have to swap again with its parent. So here you can see the heap property is satisfied. So no need to swap. So that's why no need to swap or exchange again. And the previous example that we have discussed, here you can observe this one. So we are swapping the elements until the newly inserted element reaches at the root. So this is one example. So simply add the element at the end, then if the heap property is violated, swap until the heap property is satisfied, or we reach at the root. Or simply if we consider two steps, insert at the end, then swap the elements until the heap property is satisfied. Clear? So I hope this one is clear to everyone. So formally we can write the steps that we are following for heap insertion. So I can write here the steps for heap insertion. Okay. So what are the steps? So we are writing all the steps here formally. So the first step is increase the heap size by 1 to make room for the new element. To make room or space for the new element. So first we have to increment the size of the heap by 1. Then what is the second step? Insert the new element at the last position in the array. So insert the new item or the new element at the last position in the heap. So we have an existing heap, then insert the new element at the last position of the existing heap. Then in the third step, what we will do? So we will compare the element with its parent. So we will write here the third step. Compare the element means newly inserted element with its parent, with its parent. If it is out of order, if it is out of order, swap them. What is the next step? So continue the swapping until the heap properties satisfy or we have reached the root. So here we can write continue swapping or exchanging the elements. Swapping up. Up means we are moving towards the root until the heap property is satisfied or the root is reached. So if you observe, this is like a redundant statement, or the root is reached. So if you want, you can write, otherwise you can remove this. So continue swapping until the heap property is satisfied. Okay, so these are the formal statements or steps we are following to insert a new element or new item into an existing heap. So we have to follow these 4 steps. So now we can write the pseudocode for these 4 steps, or formally the algorithm. These are the steps in English we have written. So now we can represent the formal algorithm following these 4 steps. So now we formally write the algorithm. So it is like algorithm insert. So we have one existing heap and we want to insert the new element. Assume the new element is value. So now what is the first step? Increase the heap size. So heap size equal to heap size plus 1. Then what is the next step? Insert the new element at the last position of the heap. So assume I is the heap size. So first we increment the heap size by 1 and assume I is the incremented heap size. So we have to assign the value that we want to insert at the last position. That means heap of I. So if heap is the existing array, we want to insert the element that is value at the last position. Last position means at index I, because I is the index after incrementing the heap size. So here we can write heap of I equal to value. So I hope this one is clear to everyone. So first we increase the heap size here in the first statement here. Then we are assuming I is the value of the incremented heap size and we are inserting the element that is value at heap of I. So where heap is the existing array or existing heap. So these 2 steps are clear. So I have written these 2 steps like this. Now what we will do, we will compare the element, that means the newly inserted element, with the parent, and if it is out of order, swap them, and we will continue the swapping until the heap property is satisfied or the root is reached. So we can write like this, these steps. So while the I value is greater than 1 and so this I value greater than 1 means we have not reached at the root. So the root index is 1. So while I greater than 1, that means we have not reached at the root. So while I greater than 1 and heap of I greater than heap of I by 2 floor. That means if heap of I greater than heap of I by 2. So I by 2 means here the parent node. So if the child value is greater than its parent value, then swap. So I am writing this one. So here this condition is for comparing the child with the parent. So we have earlier discussed that I by 2. So if one index is at, if one element is at index I, then the parent node is at index I by 2 or the parent element is at index I by 2. So we have written the same thing here to compare the values of its child, of a child with its parent, and if the child value is greater, then we have to swap. So if these two conditions are there, we have not reached at the root and the child of I greater than the parent of I, then we can swap. So let me use a different color here. Swap heap of I with heap of this I by 2 floor. Okay, so we have to simply swap. Then again we have to check this with the newly or the new position of the value. So once we swap, so here you can see the example. So once we swap here, so here we have swapped. Then after swapping, again we have to check whether this value and this value are satisfied or not. So here you can see the example, this one. So 90 is inserted here and swapped. So after swapping, again we have to compare whether 90 is greater than its parent or not. So if 90 is, that is the newly inserted element, is greater than its parent, then again we have to swap. So for that, here we are considering I and this one is I by 2. Now after swapping, again we have to check. So for that, we can make this as I. So I am writing here in a different color. So initially we are comparing this one as I and this one as I by 2, and we are checking. So whether the index that is at I is greater than I by 2 or not, and we are swapping accordingly. Now once swapped, again we have to check this value and this value. So for that, we can consider this one as I and this one as I by 2. So I am simply writing this here in the algorithm. So after swapping, we can make this as I, new I value is equal to I by 2 floor of I by 2. Floor we are taking because for odd numbers we have to find the parent also. So, this is the algorithm for inserting a new element into an existing heap, and these 4 steps we have to follow, and these 4 steps here we have written. So, these are the first 2 steps and these are the last 2 steps, or this is step 1 and 2 and this is step 3 and 4, and these blue color statements are within the loop. So, I hope this is clear to everyone. So, now we will discuss about the time complexity. So, how much time required? So, let me write this one. What is the time complexity for this algorithm? So, here you can see this one takes a constant amount of time, heap size increment, I equal to heap size, this is also a constant amount of time, heap of I equal to value, so this is also a constant amount of time. Now, while I greater than 1 and heap of I greater than heap of I by 2, so here we have a loop, and inside the loop we are comparing the parent value with a child value with its parent value, then swapping. So, how many comparisons are required, or how many times the loop is going to execute, or we can say the maximum comparisons, or we want to find the number of maximum comparisons. So, here you can see, or how many times the swapping is going to be executed. So, in this example we insert the element here. So, once we insert, how many comparisons are required? So, we compare this value with this value and exchanged, then we compare this value with this value and exchanged. So, how many comparisons or how many exchange required? Two comparisons or 2 exchange. So, first one is here, then one is here. So, 2 comparisons. Similarly, here you can see another one is this one. So, here we insert. So, first how many comparisons? 1 comparison here, then 1 comparison here, then after 2 comparisons we stopped, we placed 18 here, or at max another comparison is required, 3 comparisons. So, maximum number of comparisons required we can write. So, maximum number of comparisons is equal to height of the heap So, height of the heap means the maximum path length from root to the leaf or to a leaf, and we know the height of the heap. So, let me write. So, height of a heap with n nodes is about or is approximately log n base 2. So, the time complexity of this algorithm or of insertion is order of log n base 2, or we can write like order of LGN. Clear? So, I hope the time complexity is clear to everyone. So, now we will solve some previous year GATE questions that are based on the concept that we have discussed just now. So, consider a max heap represented by the array So these are the elements in a max heap. Now consider that a value 35 is inserted into this heap. After insertion, the new heap is, so 4 options are given. So first we draw the heap so that it will be better. So the root is 40, then 30, 20, 10, then 15, then 16, 17, 16, 17, then 8, 4. So 8, 4. So new element 35 we want to insert. So 35 should be inserted at the last, that means here. So if we insert 35 here, so now we will check whether the heap property is satisfied or not. So here the heap property is violated. So for that we have to swap. So if we swap, so this becomes like 30, 20, then 10, then this 35 comes here and 15 comes here. For 10 it is 8 and 4, then for 20 it is 16 and 7. Now again we have to check after insertion whether the heap property is satisfied or violated. So here you can see the heap property is violated. So we have to again swap 35 with 30. So I am directly writing here. So here the value will be 35 and here it will be 30. Now after this insertion, so let me delete these things also for better understanding. Okay, 35, here it is 30. So now again we have to check whether, so let me move this one, yes. So let me move this one, yes. So now again we have to check whether the property is satisfied or violated. So yes, the property is satisfied, no issue. So now what is the array representation of the heap, the new heap? So it is asking for the array representation. So we can write like this: 40, then this one 35, 20. So it is 35, then 20, then these elements 10, 30, 16, 17. So 10, 30, 16, 17, then these nodes 8, 4, 15. So it is 8, 4, then 15. So which option is correct? 10, 35, 20, 10, 10, sorry 40, 35, 20, 10, 40, 35, 20, 10. So option B and D are same. Then 30, 16, 17, 6, 4, 37, 16, 17, 8, 4, 15. So this one, option B is correct. So option B is correct. So I hope this one is clear. So an existing heap is there, we have to insert one element and check the heap property and swap the elements until the property is satisfied. So we will see one more example based on this. So a priority queue is implemented as a max heap. So initially it has 5 elements. The label order traversal of the heap is like this. 2 new elements 1 and 7 are inserted into the heap in that order. The label order traversal of a heap after insertion of the element is. So the label order traversal means this one. So first 40, then 35, 20, then this one. So like this we are doing. So it is called as label order traversal. Okay, anyway. So now the label order traversal of the heap is like this. So first draw the heap. So it is 10, then 8, then 5, then 3, then 2. Then 1 and 7 are inserted into the heap in that order. So first 1 is inserted. So if we insert 1, so 1 should be inserted here. So if we insert 1, verify whether the heap property is satisfied or violated. So heap property is satisfied. So no need to exchange any element after inserting 1. Then we have to insert the next element, that is 7. So if we insert 7 here, you can verify whether the heap property is satisfied or violated. So it is violated here. So 5 and 7, the heap property is violated. So this should be greater. So for that we have to swap. So if we swap, so we are going to get the new heap like this. So 10, then 8, then 7, then here 3, 2, here 1, and here it is 5. So now after swapping again we have to check with its parents. So 7, 10. So heap property is satisfied, no issue. Then the heap is like this: 10, 10, 8, 7, then 3, 2, 1, 5. 10, 8, 7, 3, 2, 1, 5. So option A is correct. So this is also a previous year GATE question. So now we will solve another example. So the elements, these 32, 15, 20, 30, 12, 25, 16 are inserted one by one in the given order into a max heap. The resultant max heap is. So here 4 options are given. So let me draw the options. So the options are like this: 32. So this is option A. 32, 30, then 25, then 15, then 12, 20, 16. So this is option A. Option B is like this: 32, 25, 30, then 12, then 15, 20, 16. Then option C: 32, 30, 25, 15, 12, 16, 20. Then option D: 32, then 25, then 30, 12, 15, 16, 20. So we have 4 options and the elements are like this: 32, 15, 20, 30, 12, 25, 16 are inserted one by one. So let me draw the heap. So the elements are 32, 15, 20, 32, 15, 20, then 30, 12, 25, 16. 30, 12, 25, 16. So in this order the elements are inserted. So first element is 32, so it is the root, no issue. Then we have to insert 15, so 15 should be inserted here, so no issue, the property is satisfied. Then we have to insert 20, again no issue, the heap property is satisfied. Then we have to insert 30, so 30 should be inserted here. So here you can see after inserting 30 the heap property is violated, so we have to swap. That means the new heap will be like this. So 32, 30 comes here, 20 comes here, then 15 comes here. So this is the new heap. So then 12 is inserted, so 12 should be inserted here, so no issue, the property is satisfied. Then 25 is inserted, so here we have to insert 25. So if we insert 25 here, then you can see after insertion the heap property is violated, so we have to swap. So if we swap, so the new array will be, so new heap will be like this: 32, 30, 20, then 15, 12. So here we have to swap. So 25, then 20. Okay, now the next element, that is 16. So 16 should be inserted here. So after insertion we have to verify the property. Yes, the property is satisfied. So now this is the resulting heap: 32, 30, 25, 15, 12, 20, 16. So here you can see the option A is correct. So it is 32, 30, 25, 15, 12, 20, 16. So this one. So I hope this one is clear. So in this way we can insert the new elements into an existing heap. So we have discussed the algorithm, we have discussed the time complexity is of order log n. So like this.